Hey guys, this is the last lesson in Chapter 5. We're going to look at optimization and how to solve real-world problems using the skills we've learned. Optimization is one of the most common applications in calculus. Many times you'll hear terms like finding the least amount of time, the greatest profit, the shortest distance, maximum volume, minimum waste. In order for us to optimize problems like this, we first have to find a quantity that needs to be minimized. So that's one of the challenges we're going to face. What quantity is going to be minimized or maximized? And then we have to find the quantity to optimize and find all the constraints, and then write the equations for each part of the problem. So I've got bolded here. Just be sure to read the problem carefully first. Then identify the quantity to be optimized and the constraints. And if a quantity is stated to be a fixed value, this will be your constraint, which must be true regardless of your solution. Now, many of you have textbooks that talk about the primary equation and the secondary equation and how to set those up. So we'll discover those as we work through some of our problems. Here's an easy one to get us started. We want to find two positive numbers such that the sum of the first and twice the second is 64, and the product needs to be a maximum. So I see two things going on here, and what I want to do first of all is give some definition to our situation. I'm going to let X represent my first number and Y can represent our second number. So then we can use those definitions to write an equation to get started. So first of all, the first sentence says that X, the sum of the two positive numbers, sum of the first number X and twice the second number, that's Y, has to be 64. So this is my first equation. Then the product of the numbers has to be a maximum. So I know that X times Y is going to give me a maximum, and then I understand what has to be maximized. Okay, so we can take this equation, once we have the two equations, we can take this equation, and if we isolate that for Y, solve for Y, we would have 64 minus X divided by 2 that we could substitute into this product, right? So I'm going to call f of X is X times Y, but I need to put this amount in for my Y. 64 minus X divided by 2. So now I have a function in terms of X, that's the product of my two numbers, and my second number was rewritten to be represented as an expression in X. So simplifying this, we get 32X minus a half X squared. That's my product. I'm going to maximize the product. So if the product needs to be maximized, we would need the derivative of the product, which would be 32 minus X. So when is the derivative equal to 0? When 32 minus X equals 0. So that's my critical number. And then I could go through working out the first derivative test and explain or show that if X is 32, any number on this side is going to be negative, it's going to be positive, and any number on this side is going to be negative because that would be increasing, decreasing to show that I've got a maximum at 32. So if X is 32, then we need to take this expression again for Y. And if X is 32, then Y would be 64 minus 32 divided by 2, so y would be 16. Our two numbers are 32 and 16. And then it would be a good idea to go back and check for sure that 32 plus 2 times 16 actually has the sum of 64. And that's pretty evident. Example 2, this is a fence problem. A farmer plans to fence a rectangular pasture that's adjacent to the river. The pasture has to contain 180,000 square meters in order to provide enough grass for the herd. What dimensions would require the least amount of fencing if no fence is needed along the river? So this is my river's edge. And I'm going to go back and draw a picture of the situation here. So we want to have a fence that's going to be along the river, 2 sides and a length. So we could call this X, and then these two could be Y to know what's happening there. So I've got this situation. I want to know about 180,000 square meters. That's an area amount. And we want to know the least amount of fencing. So that would be a perimeter problem. Okay, so I hear 2 equations. I've got the perimeter, there goes my problem, talking and writing and thinking. The perimeter is 1x and 2 y's. And then the area is x times y. So x times y has to be 180,000 square meters. So just as before, if we solve, what are we minimizing? Least amount of fencing. So that's perimeter, which means we're going to take the secondary equation, A, area, and say that the area is 180,000 is x times y. So y is 180,000, 180 divided by x. So I renamed area in terms of y, and then we're going to substitute this amount in place of our y variable here for perimeter, because we're going to minimize perimeter. So the perimeter in terms of x would be 1x and 2 y values, which is 180,000 divided by x. So there again we have the perimeter equation written in terms of x. We can simplify that to be x plus 360,000 divided by x. Then taking the derivative to find our critical number, that would be 1, and then I'm thinking of this as 360 times x to the negative 1 power. So that would be negative 360 times x to the negative 2 power, or 1 over x squared. So setting that equation equal to 0, we have 1 minus 360 over x squared equal to 0. And then 1 is equal to 360,000 divided by x squared. So we can multiply through by x squared and take the square root of both terms. And we have 2 answers, a positive answer and a negative answer. So this is where on the first page they were talking about thinking about your constraints and your domain. So if we go back up here to our picture, you think about the domain has to be a number that's not negative. And we have perimeter. What was our perimeter? We can't have negative 600, but we could have positive 600. So negative 600 would be outside of our constraint. So we got to have something bigger. And if 600 is our critical value, that's where we had a derivative of 0, then here we would be negative and here would be positive. So definitely at 600 we have a minimum. And then we know the dimensions, because if x is 600, then y is 880,000 divided by 600. So y is 300, and that tells us the size of the pasture, the least amount of fencing. So the pasture would measure 600 meters by 300 meters. And to answer the question, the least amount of fencing, what dimensions would require the least amount of fencing, it would be that 600 meter by 300 meter. And if you wanted to know how much fencing you would need, then this would be 300, 600, 300. So we would need 1,200 meters of fencing. This one is an open box question, or we're going to create a box from a piece of cardboard, or in this case, a piece of sheet metal. It measures 18 inches wide by 30 inches long. And we're going to cut 2 squares out of each corner. And each square would be x by x. It's a square. So if it's 18 inches this way and we cut 2 x's out, this leftover piece is 18 minus 2x. And if it's 30 inches long of sheet metal and we cut 2 x's out of that side, then this side would be 30 minus 2x. So we have that visual going on. Let's see what's on our pull tab. Oh, just an example. So I've cut out these squares and turned up the corners and made a box that's open at the top. So we want to know what size squares should be cut to make the box a maximum volume, and then find the volume. So we can do that. May need our calculator. So first of all, let's talk about the volume of the box. So volume is length times width times height. Length times width times height. And we want to write our volume in terms of x. So we have a length that's 30 minus 2x, a width that's 18 minus x, and this x is our height. So we have x times 18 minus 2x times 30 minus 2x. Now I've already pre-done this, but if you have a calculator or want to stop the video, you want to expand that out to be able to take the derivative quickly. And like I said, I've already done that. So I have 4x cubed minus 96x squared plus 540x. So now the second thing is, what are my critical numbers? So we want to find the critical values to be able to determine the possible choices for the size of x. So we got to think about the domain here, right? If this sheet metal is 18 across and you fold it in half, if you cut out a square that's 9 by 9, all you've done is cut the paper into 4 pieces. So we know that the volume, or the domain for the box, not the volume of the box, but the domain of the box has to be some number in between 0 and 9. You can't cut it in half. You're just ruining the sheet metal. You've got to have a number smaller than 9. So my shortest dimension was one of the constraints of the domain. You follow that? So we want the derivative of the volume in terms of x, because that's what they're asking us to maximize the volume. So the derivative of the volume will be 12x squared minus 192x plus 540. So I'm going to factor out the 12. So 12 times x squared minus 16x plus 45 would give us 0. And unfortunately, this won't factor this polynomial. So we could divide by 12 and reduce it down a little bit. And then I'm going to complete the square. So I'm going to move the 45 out here. So we have 16 minus x squared. And I know from algebra that half of 16 is 8, and 8 squared is 64. So we could add and subtract 64 without changing the problem, and know that we have x minus 8 as a perfect square trinomial, and 45 minus 64 is negative 19. So now we can easily solve this without using quadratic formula, causing ourselves a bunch of stress. And then taking the square root of both sides, we're going to end up with x minus 8 plus or minus the square root of 19. So we have two possible answers, either 8 plus the square root of 19 or 8 minus the square root of 19. But 8 plus the square root of 19 is going to put us over that domain restriction. And that means only 8 minus the square root of 19 will work, because square root of 19 is a little bit more than 4, right? So with our calculator, I have 3.641 inches is my critical number, and that's the size that we're cutting out. But we want the volume too. So if we go back into find the volume, that x times 18 minus 2x times 30 minus 2x, the volume of 8 minus the square root of 19 is about 886.552 cubic inches. Because our measurement was in inches, right? Yes, inches. So I know the volume and I know the size to cut out of the side. If you want to do the first derivative test, or your teacher asks you to do that test, you can easily do that. At 3.641, you have a maximum because the derivative changes signs from positive to negative, and the function changes from increase to decrease. This is the volume. This is the derivative. So to clean that all up, you want to answer the question in the sentence. The volume of the box made out of sheet metal is approximately 886.552 cubic inches. And that will be maximized if we cut squares from the corners. This is from every corner, from each corner. That measure 8 minus the square root of 19 inches. And the reason that happened is because the volume derivative was 0 at that point, 3.6. And the signs changed from positive to negative there. So we're putting all of this together. Whoop. On this next slide, you're going to see just kind of we don't have the picture of the strategy. There it is. I just went too fast. Okay, so our strategy for solving optimization problems like this would be first read the problem, underline all the key information, draw a picture if you can, label everything, find the primary equation, the secondary equation, and so on and so forth. So let's give one more a try, and then we'll save that for the rest for another day. Okay, in the last few examples, we were guaranteed that the functions had absolute extrema by the extreme value theorem. So we want to watch some situations where the domain is neither closed nor bounded. So we have to think about those in a different way. Here in example 4, we want to know what are the dimensions of an aluminum can that can hold 40 cubic inches of soda, and it uses the least amount of aluminum. Assume the can is cylindrical and capped on both ends. So I've got a rough drawing here, but I'm sure if we pull this little pull bar out, we'll see how to deconstruct that right circular cylinder. So you see I have an area. We're talking about surface area here. You understand why we have to deconstruct the can? The top and the bottom is a pi r squared circle, and we have 2 of them. And then if you take the side apart and split it down the middle, down one side, you see that the area is just the circumference of a circle times the height. So if we put these together, we'll have a formula for the surface area of a right circular cylinder. So that's the first thing we're going to think about. What's the surface area formula? So surface area is 2 circles, and a circle is pi r squared. So we have a top and a bottom, plus we have 2 pi r for the circumference around the circle times the height of the can, so 2 pi r h. We also know that the volume has to be 40 cubic inches, and that we know that pi r squared h is going to be 40, because that's the volume, right? Pi r squared, the base, times the height. Volume is the base, which is pi r squared, times the height. Remember all of that from geometry, capital base times height? And if we solved for height, let's go ahead and do that here. The height is 40 divided by pi r squared. And if you're thinking about the domain, we better think about that right at the beginning here. I know that my surface area has to be a positive surface area, and that we're definitely holding constant the 40 cubic inches for the volume. So the next thing we want to do is to be able to write our surface area formula in terms of the radius, because we have this term here. So how can we do that? We'd have to eliminate the h. We need to get rid of this term by substituting 40 over pi r squared h. So our surface area in terms of just radius is 2 pi r squared plus 2 pi r h. So our h value is 40 divided by pi r squared. You with me so far? And then simplifying that, the surface area in terms of the radius is 2 pi r squared plus 2 times 40, that's 80. And then one of our pi r's is going to cancel the other pi r and just leave us an r in the denominator. So we can take the derivative now and find our critical number for the radius. So surface area derivative is 4 pi r minus 80 divided by r squared. So 4 pi r, we're going to set this equal to 0. So I'm going to do 4 pi r and add 80 over r squared to the 0. And then simplify. So we have r cubed is 80 divided by 4 pi. Or r is the cube root of 20 divided by pi. So on our calculator, the radius is about 1.853 inches. So now we have a radius. And again, if you check, let's see, this was solving for 0. And then if we check on our number line, we have to have a domain bigger than 0. And we're cutting out, or we're making the radius 1.853 inches. So the derivative of the surface area is negative on this piece and positive on this piece, which verifies that we have a minimum. We wanted to minimize the amount of aluminum, but now we need to know what the height is. So our height formula was back here, 40 divided by pi r squared. So the height of the can is 40 divided by pi, and then r was the cube root of 20 over pi squared, pi r squared. So let's figure that out on our calculator as well, which is about 3.707 inches. So a word here. You notice how each time I found a calculation, I went back to the original. Instead of rounding here, I'm using the exact value. That's a wise thing to do on the AP exam, because you don't want to take this rounded answer and then plug that rounded answer here and come up with the wrong answer on a free response question. So now we can answer the question in a sentence. We know that the can, or the soda can, measures, we can either say the approximate or the exact. So I'm going to give the exact, measures the cube root of 20 divided by pi inches, and the height is about 3.707 inches. And this was about 1.853 inches. So we've given them both situations. And the reason we know that this is the truth is because the derivative of the surface area for the 1.853 was 0. And the surface area with respect to the radius, that rate, changed signs from negative to positive there. From negative to positive. So you've seen 4 examples here today, and we'll do the rest of them, 5, 6, and 7. We'll do those tomorrow. They're a little more complicated. See you then.